This is the 7th lecture in general chemistry, and the title is Balancing Chemical Equations and Chemical Problem Solving. This is all material from chapter 3 in the book. This is really what I would say more or less review material. If you've had high school chemistry, this should all be review material. So if you're comfortable with it, maybe you don't have to spend a lot of time on this material. If you're uncomfortable or never had general chemistry in high school, this might be something you want to spend some more time on, because everything we do after in this class builds off of this chapter. And just wanted to briefly mention the pattern we're going to follow in this course. This is specifically from fall, so this the material for each exam is going to be a little bit different here in this class in the summer. But I wanted to point out that we are starting chapter 3 material, which would normally be sort of the new section of material between exam 2 and exam 3 in fall. But how summer's set up, just the way the timing works, chapter 3 is going to be included in the material that's with exam 2. Okay, so and it really doesn't match very well with the material that is covered in exam 2, but that's just the way we have to do it. But everything else that we're going to do at the third week of this course is going to build off of chapter 3, and that would be chapter 4, chapter 5, and chapter 6. So I just wanted you to be aware of that, and it's the material from chapter 3. There'll be some material on the second exam, but probably more importantly on the third exam. Right. So let's look at chapter 3 in depth. The first section covers the mole. We're not going to be covering the second section in this class, but then we're going to cover the third and the fourth sections as well. Balancing chemical equations, and then calculating quantities of reactant and product. Okay, but let's first talk about the mole a little bit. And this is a slide we've seen before in this class and during the first lecture. But now, technically, we're gonna know what a mole is, right? And again, that's just the number of anything that is the same number of atoms that are in 12 grams of carbon-12, and that's this number, 6.02 times 10 to the 23rd. That's also known as Avogadro's number, right? And again, a mole is just simply a quantity of something. It can be anything, right? And we use the term entities, and typically in this class, we're talking about atoms or molecules for the most part. And to 4 sig figs, it's 6.022 times 10 to the 23rd. All right. And this figure in your book just shows a mole of some familiar compounds. Right? And you can see that sugar is a much bigger molecule than something, so here's sugar, and something like salt is a much smaller molecule, so a mole of sugar is going to have a larger volume. It's going to look bigger, right? And then a mole of water is 18 grams, and the density of water is 1 gram per milliliter, so a mole of water is 18 milliliters. Okay. And the term molar mass, right? A molar mass is the mass of 1 mole of whatever you're referring to. So if it's a molar mass of an element, that would be the same as an atomic mass. If you're talking about a molar mass of molecules, it'd be a molecular weight, right? That's what it would normally be referred to as, right? And that is just the amount of something that is required to make a mole, how much of that something, how much it weighs. Right? And the easiest ones to look up are those for elements, because they are the molar mass, which would be the atomic weight for an element, that's given to you on the periodic table. Right? So those are fairly easy to work with because you just look up a number. Molecules, that's probably what we're going to be looking a little bit more at in this class. To calculate a molecular weight for a molecule, you just add up all the atomic masses, all the atomic weights, the molar masses for those elements from the periodic table. However many of those atoms are in your element, you just add them up. And don't worry, we'll get some practice doing that if you're uncomfortable with that. But hopefully most of you have already done this, and this is really easy in review for you. All right. So for molecular elements and for compounds, the formula is needed to determine the molar mass. Right? And what we mean by that, for molecular elements, sometimes you have diatomic molecules formed by the molecular element. Something like oxygen, it exists as O2 in the natural world. Right? So oxygen, to find its molecular weight, we'd have to multiply the atomic mass of oxygen by 2. Right? And if you look at the periodic table, you see that the atomic weight, the atomic mass of oxygen, is 16 grams per mole, approximately. Sometimes it's written as like 15.99, but for simplicity in this class, we can just call that 16. Right? So the molecular weight of oxygen gas, O2, would be 2 times 16 grams per mole, and that gives us 32 grams per mole. Right? If we look at something a little bit more complicated, a molecule that has more than one element in it, so this would be considered a compound, SO2, sulfur dioxide. Well, to calculate its molecular weight, right, there's 1 sulfur, so we multiply 1 by the atomic mass of sulfur, and then we add 2 times the atomic mass of oxygen. Right? So in a sense, we're just adding up the atomic mass for every atom that's in that compound. Right? And looking at the periodic table, sulfur, that the atomic mass of sulfur is 32, and 2 times 16 for the 2 oxygens, that's also 32, so 64 grams per mole would be the molecular weight of SO2. And if we look at a chemical formula for a compound that's a little bit more complicated, glucose, that chemical formula is shown here, C6H12O6. Right? Now, if we add up all those atoms and their atomic weights, the molecular weight is 180, basically 180 grams per mole. Right. So if we look a little bit closer at this formula, what kind of information is contained in that formula? Well, we know that these subscripts, that tells us the number of atoms that are in a molecule of the compound. So C6, that means there are 6 carbon atoms for every 1 molecule of glucose. There are 12 hydrogen atoms for every molecule of glucose, and there are 6 oxygens for every molecule of glucose. The other way you can use these numbers is they also stand for the number of moles of atoms per mole of the compound. So there'd be 6 moles of carbon atoms if you had 1 mole of glucose. In the same fashion, there's 12 moles of hydrogen atoms in a mole of glucose, and there's 6 moles of oxygen atoms in a mole of glucose. And then as we're going to see in a couple slides here, you can convert from moles of something into number of atoms of something by multiplying by Avogadro's number. Right? And you can also calculate the mass of something by multiplying by the atomic weight. And that's something that we're also going to be doing. And so that brings us, how do we interconvert between moles, mass, and number of chemical entities, right? So if we're given a mass, or if we should say if we want to calculate a mass, we have to multiply the number of moles of a compound by the molecular or atomic weight, right? And so that's in units of grams per mole. So if we have moles times grams per mole, the moles will cancel and we're going to be left with grams, right? And that gives us a mass. Right. Now, if we want to do the opposite, if we're trying to calculate number of moles of something, we would take our mass, and this is a little bit confusing on this slide because it's multiplying by moles over grams, which would be the same as dividing by molecular weight, right? So this is the inverse of the molecular weight, right? So you multiply by the inverse of the molecular weight, or let's just say divide by the molecular weight. That's a little bit easier, right? And if we're trying to find the number of entities, let's say the number of atoms or the number of molecules, right? We calculate that by finding the number of moles of something, and we multiply that by Avogadro's number, right? So number of moles, let's say of an atom, and Avogadro's number is 6.022 times 10 to the 23rd atoms per mole. So the moles would cancel and we'd be left with atoms. Okay. And you can also do that if you know the number of atoms, calculate the number of moles by dividing by Avogadro's number. Right. And so that's probably, I think it's a little bit easier to show it in this visual, right? And this is kind of a roadmap for you to use. So let's say we're given the mass of an element, and we want to find the amount of the element. So we want to go from the units of grams to the units of moles. That's when we use the molecular or atomic weight, the molar, what we more generally refer to as the molar mass, right? So since we're talking about elements, that would be atomic weight, right? So to get from mass in grams to moles, we would take the mass and divide it by the molecular weight to get moles. If we wanted to do the opposite, we had the number of moles, we wanted to calculate the number of mass, we would multiply by the amount by the molecular weight to get mass, right? And the same sort of thing for Avogadro's number. If we're trying to convert from moles to atoms or molecules, we would multiply the number of moles by Avogadro's number to get atoms. If we had the number of atoms, we would divide by Avogadro's number to get the number of moles. Right, so let's try a couple problems. First problem, dealing with silver, and we are told that we have 0.055 moles of silver. How many grams are in 0.055 moles? Right. So this one, it's very simple, right? We have the number of moles, 0.055 moles, and we need to get number of grams, so we're going to use molecular weight. And in this case, we're talking about silver, so we look up on the periodic table and find the atomic weight of silver. And that is 107.87 grams per mole. Right? And if you didn't know you had to multiply this, what I would recommend doing is before you write down the multiplication symbol, look at your units, do dimensional analysis. Right? So we're given the number of moles, the atomic weight is in grams per mole, and we want to find our answer, ultimately we want in grams. So what mathematical relationship can we use to get our final answer in grams? Well, that would be multiplying these two numbers together, right? So that's how you can check if you're sort of doing this work right. In a sense, let me just back up this slide. You don't have to memorize whether you need to, using molecular weight or atomic weight, you don't need to memorize if you need to divide or multiply. You can just look at the units and that will tell you. Okay. So when we do that, we're going to get 5.93 grams of silver in 0.055 moles. Okay, let's try another question, similar question. How many lead atoms are in 5.97 times 10 to the minus 3 moles of lead? Right. So we're given number of moles. That's a bad zero. 0.00597. And that's moles of lead. Right. And we're trying to find atoms of lead. Right? So this is when we're converting from amount to number of entities. So we need to use Avogadro's number. Right, so let's just write down Avogadro's number, 6.022 times 10 to the 23rd. And that would be in the units of atoms per mole. Right? And so we need atoms. We want the moles to cancel, so how do we do that? We simply multiply the numbers together. And the moles will cancel. And what we get is 3.6 times 10 to the 21 atoms of lead that are in 0.00597 moles. Okay, last practice in this sort of basic beginning of chemical problem solving. Right? Iron is the main component of steel. It is therefore the most important metal in society. Well, that's kind of a, that's more of an opinion, I guess, but it's also essential in the body, so we'll just go along with that. How many iron atoms are in 10 kilograms of iron? All right. So we're given a mass this time, and we need to calculate the number of atoms. And this has two kind of new tricks to it, right? This is really where you need to remember. Let's go back. This diagram, right? We're given a mass, right? And we want number of atoms. You can't calculate number of atoms directly from the mass. You have to first convert it into moles, then calculate the number of atoms. Right? That's can be a very tricky thing for students. There's lots of mistakes are made by skipping that step. Right? And then the other thing that's a little tricky in this is that we're given number of kilograms, not the number of grams. Right? So that's another hang up. So really the first thing we need to do is to convert our mass into grams, because that's what the molecular weight, the atomic weights, those are in grams per mole, not kilograms per mole. And this is something you probably can do in your head. If you're at all uncomfortable, just write it out and do dimensional analysis, right? There are 1,000 grams per 1 kilogram. So we're multiplying by 1,000 and we get 10,000 grams. Right, so kilograms cancel. Right, so that's the amount of iron we have. Right. We then determine from the mass, we convert into number of moles. And we do that by dividing by the atomic weight of iron, 55.85 grams per mole. Whoops. Grams cancel. 1 over moles would just be moles, right? So we get 179 moles of iron. And then converting from number of moles to number of atoms, we multiply by Avogadro's number. And we get 1.08 times 10 to the 26th atoms of iron in 10 kilograms. Okay. Well, the other thing that we can do, if we're giving a mass of a compound, we can convert it into the moles of a compound. And then using the chemical formula, we can convert from the amount of the compound to the amount of a particular element that's in the compound. And the way we do that is by using the chemical formula. And that table that we showed for glucose, that's what we were in a sense doing at the bottom of that table. Using the chemical formula to determine the moles of an element in that compound. Okay, so let's try another practice question. Nitrogen dioxide is a component of urban smog that forms from the gases in car exhausts. How many molecules are in 10 grams of nitrogen dioxide? Right, so this is essentially, we're trying to find how many molecules are in 10 grams of a compound. Right, so this one, it's very similar to what we've done before with atoms, but we can't simply look up well, I suppose you can if you have Google, you can look up the molecular weight of nitrogen dioxide, but on an exam, you'd have to calculate that. So how do we calculate that? Well, first we look at the chemical formula. Nitrogen dioxide is NO2, right? Then we have to calculate the molecular weight. Okay, so the molecular weight, I'll just write it under here, it's going to equal the atomic weights of the atoms in this compound. So for nitrogen, that's 14 grams per mole. And then oxygen is 16 grams per mole, but we have 2 of them. 2 times 16 grams per mole. Right, so that's what we add up for this molecular weight, and we get 46 grams per mole. Right, so that's the molecular weight of NO2. Right. Then to find the number of moles of this, we take the mass that we have, 10 grams. We have grams per mole. Our final answer we want to be in moles. Or I guess not final. What we're trying to do is calculate the number of molecules. So we need to find the number of moles first. So to do that, we would take the mass we have, 10 grams. We divide it by our molecular weight, 46 grams per mole. And that will give us our number of moles. Whoops. 0.217 moles of NO2. And then we multiply that number by Avogadro's number, 6.002 times 10 to the 23rd, and we get 1.3 times 10 to the 23rd molecules. Okay. The other thing the book talks a lot about is calculating mass percent in either a percentage or as what they call a mass fraction. And the way that I would recommend doing it is shown here. The mass percent of an element that's in a compound, let's just call that element A, is going to be equal to the number of atoms of A that are in the formula for that compound. Multiply that by the atomic mass of A and divide it by the molecular mass of the compound. Right? So that would give you, if you just did that, that would give you the mass fraction of A. When you multiply by 100, that will give you the mass percent. Right? The book also explains doing it this way. I don't recommend doing it this second way, but if you want to, some of you might find that easier. So I just kept it included. All right. Let's try a practice problem determining mass percents and mass fractions. Right? And in this, we're talking about magnesium nitrate. Okay. And so the formula of magnesium nitrate, magnesium would have a +2 charge. Nitrate, NO3, has it's what we call a molecular ion. NO3 has a -1 charge. So to balance that, you have 1 magnesium atom and 2 nitrate, 2 NO3 molecular ions. Right? So the formula is shown here. So let's look at magnesium first and find the mass percent of magnesium in magnesium nitrate. Right? So going back to this, the number of atoms of magnesium times the atomic mass of magnesium divided by the molecular weight of the compound. All right, so magnesium, we have 1 atom of magnesium times 24.3 grams per mole. That's from the periodic table. Right? And then we divide by the molecular weight. All right. And so let's calculate the molecular weight up here. Magnesium is 24.3 grams. Nitrogen is 14, but we have 2 of them. And then oxygen is 16 grams per mole, but there's 3 for every nitrate, and we have 2 nitrates. So that would be a total of 6 oxygens. So 6 times 16. And that comes out to be 148.3 grams per mole. Okay, and it keeps skipping forward. Okay, so we divide that by 148.3 grams per mole. And that gives us 0.164. Right? And that would be the mass fraction. If we multiply that by 100, that will give us the percentage, mass percent. So that'd be 16.4%. So magnesium nitrate is 0.164 or 16.4% magnesium by weight. Okay. If we do that for the other atoms, for nitrogen, we would have 2 times 14 grams per mole divided by 148.3, and we get 0.189 fraction, or 18.9%. And oxygen, you should get 6 times 16 divided by 148.3 equals 0.647, or 64.7%. And if you add up all the fractions, mass fraction values, you should get a number that's 1, basically. And if you add up all the mass percentages, they should add up to 100%. Mass fraction can also be used to calculate the mass of a particular element in any mass of a compound, right? And all you would do with that is if you had the mass of a compound and you had the mass fraction of an element in that compound, you just multiply those together to get the mass of any element that you're looking for. So if we try a practice problem using the information we just found out in problem 5, determine the mass of nitrogen in 50 grams of magnesium nitrate. Right? So we have 50 grams of magnesium nitrate. We multiply that by the mass fraction of nitrogen in magnesium nitrate, and that was 0.189. And we get 9.45 grams of nitrogen in 50 grams of magnesium nitrate. And it's very important to remember to use mass fraction for that and not the mass percentage, or you're going to get a larger number than the total mass of the compound. Okay. Moving on to section 3.3 and 3.4. Right? So 3.3 deals with writing and balancing chemical equations. Hopefully this is, again, sort of a review for you. If this isn't, if you haven't ever taken high school chemistry, this is really something to spend a little bit more time on, but I'm assuming most of you have taken high school chemistry, and this is really something that you cover a lot. This idea of chemical equations and balancing chemical equations. So really what a chemical equation does is it uses formulas to express what chemicals are reacting and the quantities that they're reacting in, the ratios that they're reacting in. And so this figure from the book, really it's telling you the macroscopic level and the microscopic levels. And what they mean by that, switch to laser pointer. So this would be the macroscopic level of this reaction. If we have hydrogen gas and fluorine gas to mix and make hydrogen fluoride, right? So the ratio in which they react is 1 mole of H2, 1 mole of F2, and 2 moles of they make 2 moles of HF. Right? Well, that ratio, you can say they're 1 mole of each other, or you can say at the simplest level that equals a 1 molecule to 1 molecule ratio. Right? And the way we would write that is by this chemical equation at the bottom. So we just simply have H2, the G in parentheses stands for gas, that's the state of matter it's in. So H2 gas plus 1 F2 gas goes to 2 HF gases. Right? And that 2 can stand for 2 moles of HF or 2 molecules of HF, depending on how you look at it. Okay. Another more complex reaction would be the combustion of octane. Right? So octane is here, C8H18. Right? So the chemical equation for that, the balanced chemical equation, is shown below here. Right? Obviously, a little bit more complex than the hydrogen and fluorine gases combining. Right? And another reaction that your book is showing you is this idea of magnesium and oxygen making magnesium oxide. Right? So magnesium's a metal, oxygen's a gas, and they form an ionic compound, an ionic solid, magnesium oxide, right? And the ratio would be 2 magnesium atoms plus 1 molecule of O2, and that would give you 2 what we would call formula units, because it's an atomic compound. You can really sort of think of them as molecules, but 2 formula units of magnesium oxide. Right? And you'll see that on both sides of that arrow, then there's 2 magnesium atoms and there are 2 oxygen atoms on both sides, so that the equation is balanced, right? And so if you were trying to balance this from scratch, you first would write out magnesium plus oxygen goes to magnesium oxide, and then you would look at each atom and try to balance that. So reactants are written on the left, products are written on the right, and there's a yield arrow. So that arrow is telling you the transition from reactants to products. Right. So the equation must be balanced. You have to have the same number and same type of each atom on both sides of the arrow. So first, there's how do we balance a chemical equation? Well, the book gives us several steps to follow, and the first is translate the statement. And that's if you're not given a chemical equation, you have to translate words into a chemical equation. So if we get the statement magnesium and oxygen gas react to give magnesium oxide, we translate that statement into Mg plus O2 goes to MgO, excuse me. Right, so that would be translating it. Next, we balance the atoms using coefficients. Right? You can't change a formula, a chemical formula, but you can write different numbers before that chemical formula. Right? So in this case, let's look back here. So oxygen has a 2 in its chemical formula, O2. Right? Magnesium oxide, though, only has 1 oxygen. So to get oxygens to balance on both sides, we have to write a 2 out in front of magnesium oxide to give us 2 oxygens on both sides of the arrow. When we do that, we'll have 2 atoms of magnesium on the product side, but only 1 atom of magnesium on the reactant side. So we have to write a 2 out in front of magnesium on the reactants. And so we get this. The next step is to adjust coefficients if necessary. Now this is only done if you have coefficients in front of every compound or molecule that are divisible by a common denominator. So in our case, O2 has a 1 in front of it, so this is fine. If they all had 2's in front of them, you then divide by 2 and simplify it. Okay. Check that all atoms balance, and they do. And then finally specify states of matter, and that's also very important. And that's very important to do in the online problem sets as well, because it won't count them correct unless you do that. Right? So in this case, magnesium would be a solid. We write that S. Oxygen's a gas, and magnesium oxide is a solid. Okay, so let's try a practice question. Right. So the metabolism of glucose is very much like the combustion of glucose. So what a combustion reaction is, it's when something combines with, typically a hydrocarbon, combines with oxygen, and it forms CO2 and water. Right, so we're going to talk a lot about combustion reactions, and that's what they are. They're combining with oxygen to form CO2 and water. Right, so let's follow the plan and balance this chemical equation. So translate the statement. So the combustion of glucose, we would write that as C6H12O6 plus O2 goes to CO2 plus H2O. Okay. Now we have to balance the atoms. In something like this, it looks a little bit complicated, but we only have 3 different types of atoms in these molecules, so it really isn't as bad as it seems. The real problem is oxygen is combined in all 4 of the molecules. The 2 reactants and the 2 products all have oxygen, so it's a little bit tricky to balance oxygen. So I would recommend first looking at either carbon or hydrogen and starting there. So let's look at carbon. There are 6 carbon atoms on the reactant side. So to make that balance for carbon, we would write a coefficient of 6 out in front of CO2. When we do, I guess first, the next step, again, not looking at oxygen, let's look at hydrogen next. We have 12 hydrogens on the reactant side. To get 12 hydrogens on the product side, we'd have to write, again, a 6 out in front of H2O, right? 6 times 2 would get 12 hydrogens, right? So carbon and hydrogen are now balanced. The other thing we have to do, the last thing, is balance oxygen by writing a coefficient out in front of O2 on the reactant side. So how many oxygens do we have total as products? 6 times 1 in H2O, that's 6. And 6 times 2 in CO2, that's 12. So 12 plus 6 would be 18. So we need a total of 18 oxygens on the left side. We already have 6 in glucose. So we're going to need a total of 12 more. To get 12 more, we have to write the coefficient of 6 out in front of O2. Right? So that would be the balanced chemical equation for this reaction. Right? We don't have to adjust any coefficients because there are no divisible, no common denominators, right? Because we have a 1, in a sense, their coefficient is 1 in front of glucose, so that's simplified. You can check and see all atoms balance. And then the next thing would be to specify the state of matter. So let's just rewrite this again, C6H12O6. And let's just call that a solid. Plus 6O2 gas goes to 6CO2 gas plus 6H2O liquid. Right, so that would be the full balanced chemical equation. A term you hear a lot is stoichiometry, and that really stoichiometry means just the ratios of compounds in a chemical reaction, and you get that from the balanced chemical equation. And you can use these ratios, these stoichiometric ratios, in calculations. Right. Again, these coefficients are from the balanced chemical equation, and they represent the number of reactant and product particles, either molecules or moles, that react with each other. Right, and that's, you can use both mass and moles because the moles and mass are related, right? The mole ratios from these balanced chemical equations really can be used as conversion factors. And we're going to do a few practice questions that involve this. So if we look at a balanced chemical equation, in this case we have C3H8 gas plus 5O2 gas going to 3CO2 gas plus 4H2O gas. So this is a combustion reaction. Right. So if we look, that's the chemical equation. And what do we want to view this in terms of? Well, we can view this in terms of molecules. Right? From this balanced chemical equation, right, we have one molecule of C3H8. We have 5 molecules of O2, and we have 3 molecules of CO2 and 4 molecules of H2O. So you can view these numbers in the balanced chemical equation as if they were molecules. You can also view them as if they were moles, right? And that stems from the fact that you can convert molecules into moles of something by dividing by the Avogadro's number. If you did that to all of these, all 4 atoms in this chemical equation, you're going to get the same exact ratio, right? You can also do this in terms of mass. So if you take the number of moles times the molecular weight for each of them, you would get 44.09 for C3H8, 160 for O2. If you add those together, they should equal out to 204. And if you do that to the product side as well, the total mass of the products is equal. And again, that stems all the way back to when we talked about in the first lecture, the conservation of mass conservation. And it shouldn't be surprising. You have the same number of atoms on each side of the arrow. So they're just combined a little bit differently, but they're still there and they still have the same atomic masses on both sides. So the total mass should be the same. And that brings us to this figure. And I think this is probably one of the most important figures to understand in the class. And it looks very similar to something we've already looked at. So we've sort of looked at the left side of this, if you want to just think about that. This is a roadmap for you to solve almost any chemical problem that we're going to face from now to the end of the quarter, right? And typically, in a chemical problem, you're going to be given enough information to calculate the amount of one of the compounds in the chemical reaction, right? And then you convert from the amount of, let's say, of compound A into the amount of compound B. And you do that by using the ratio, the molar ratio from a balanced chemical equation, right? And once you do that conversion, then you can convert into the mass of that compound or the number of molecules of that compound, whatever the question's really asking for. So just as an example, typically you're going to be given the amount of the mass of a compound, and you're going to be told what reaction is occurring. And then it's going to ask you for the mass of another compound, maybe a product of the reaction. And so how you calculate that is you convert mass into amount using the molecular weight of compound A. Then you use that molar ratio in the balanced equation to get the moles of compound B, and then convert moles to mass using the molecular weight of compound B. Right, so that's typically the roadmap that you're going to follow. So let's try some practice questions. All right, methane is natural gas. It's converted to CO2 and water in combustion. Again, it's a hydrocarbon. This reaction also gives off heat, which can be used to heat air. That's how your furnace works. probably, unless it's really old. But, all right, the question itself, what is it saying? How many moles of oxygen are required to combust 7 moles of methane? Right, so in this one, we don't have, we're not given a chemical equation. So we have to translate this statement into a chemical reaction and then balance that chemical equation. So this is simply a combustion reaction with methane. Right? So what is a combustion reaction, right? That's something combining with O2, and that something is a hydrocarbon, I should say, combining with O2, and it's going to be forming CO2 and, and water. Okay, so that's our translation. Our balancing, how do we balance this? Well, the hydrogens, we have 4 hydrogens on the reactant side. We have to have 4 on the product, so we need a 2. When we do that, we're going to have a total of 4 oxygens and of product. So to get 4 oxygens on the reactant side, we add a 2 there, right? So we're good, we're balanced. Right. So the question's asking for how many moles of oxygen are required. So let's just write a question mark there under the oxygen to combust 7 moles of methane. So methane, we have 7 moles. Okay. So this is, some people get a little confused here, but really you can convert the number of molecules between these four compounds, or you convert the number of moles directly. Right? And if we think back to our roadmap, if we're trying to get amount of compound A into amount of compound B, that all we use is the molar ratio from our equation, right? So you can think of this as a conversion. 7 moles of CH4 and just do like you would the dimensional analysis, right? And the ratio, given the chemical equation, we have a 2 in front of O2, so we get 2 moles of O2 for every 1 mole of CH4. And so those are the coefficients straight from this chemical equation. So we're going to get 14 moles of O2. Okay, so that's simple. That was fairly easy because the question is giving us the number of moles of methane and asking for the number of moles of oxygen. What happens when it gets a little bit trickier? Right? So how many grams of CO2 form when 10 moles of methane is combusted? So let's remind ourselves of that balanced chemical equation. And pan is not working, so hold on, I'll pause it. I'll try to figure this out. Okay, so let's try this again. Let's write this equation. CH4 plus 2O2 goes to CO2 plus 2H2O. Okay, so that's a balanced equation. What we're given is that we have 10 moles of methane. Whoops. And I forgot about this. Sorry. We have this the roadmap shown here. All right. So amount of methane, we're given that. So that's 10 moles. All right. Then we use the molar ratio as a conversion factor. So 10 moles of methane, convert that into moles of CO2, and this is simple because it's 1-to-1 ratio. And you might not even need to write this out, but when we're learning here, I think it's important to just to remember how it's done when you get some other fraction that's different. Right? So 10 moles of methane is going to turn into 10 moles of CO2. And then we multiply by the molecular weight of CO2, which is 44 grams per mole. So what we get out as the mass would be 440 grams of CO2. Okay, and then another practice question along the same line, but now we're not given the number of moles to start. We're given the number of the mass, right? So the same reaction, combustion of methane, how many kilograms of oxygen are required to form 2.86 kilograms of H2O? Right. So just remind ourselves, CH4 plus 2O2 goes to CO2 plus 2H2O. And we're given 2.86 kilograms of H2O. Now remember, if we're given kilograms, we have to convert that into grams. Okay, and that's just multiplying by 1,000. So that's 2860 grams of H2O. So we have 2860 grams of H2O. We divide that by the molecular weight of water, which is 18 grams per mole. And that gives us approximately 158.9 moles of H2O. Okay. Then we convert, the question's asking for the oxygen, so we convert moles of H2O into moles of oxygen. So let's do that over here, 158.9 moles of H2O. Write our conversion factor. So there are 2 moles for oxygen for every 2 moles H2O. So it's really just a 1-to-1 ratio again. And I really prefer to write these out because then you can see that the moles of H2O cancel. If those numbers were anything more complicated, like a 7 and a 9 or a 6 and a 14, whatever, you would know which one to put on the bottom and which one to put on the top. That's the biggest thing that's messed up. People will divide instead of multiply in a sense. And the way to really prevent that is to write everything out, the units very explicitly. Okay, so that's just multiplying by 1, so 158.9 moles of O2. So the question isn't asking for the number of moles, it's asking for the mass. So we multiply that by the molecular weight, so that would be 2 times 16 grams per mole. And let's do that real quick. 158.9 times 32, we get 5,084, basically 5,085 grams of O2. Question's asking for kilograms, so we convert that to kilograms. That'd be 1 kilogram is 1,000 grams, so dividing by 1,000. So basically 5.09 kilograms of oxygen would be required to produce 2.86 kilograms of H2O. A lot of times you'll see reactions that are occurring in sequence. And when that happens, the product of one reaction becomes the reactant in the next reaction. You can write an overall reaction for these, no matter how many steps, how many individual reactions that are occurring in this sequence, you can write an overall reaction. And to do that, I like to think of it as adding these reactions together. And what happens is that if you have a substance that forms in one reaction and reacts in a subsequent reaction, you can cancel those out. They can be eliminated. So if something's the same on both sides of the arrow, it can be crossed out. And then you add up whatever's left. Right. So let's try a overall, going through this overall reaction for a reaction sequence. So the problem is roasting is the first step in extracting copper from this calcite mineral. In the next step, copper 1 oxide reacts with powdered carbon to yield copper metal and carbon monoxide. We're trying to write a balanced overall equation for this two-step process. So let's see the individual steps. So if we look, these are the two individual steps. So we have our mineral, roasting it with oxygen, sort of like a combustion reaction, but this is not a hydrocarbon. And we get copper 1 oxide in SO2 gas. That copper 1 oxide is then reacted with solid carbon to form copper metal and carbon monoxide gas. So what do we see on both sides of the arrow? Let's see. C2O, copper oxide, we see on both sides of the arrow. Oh, sorry, first we're balancing. All right. So we balance the equations. We look on each side of the arrow and we see that this copper oxide is on both sides. So we can cross that out, right? That was the only compound that was on both sides of the arrow. So then we add up everything else. So all the reactants are added together, all the products are added together, and we get the final balanced equation for the overall two-step process. And that's shown here. Okay. Right, the last concept the book talks about is limiting reactants. Right? And so far we've just sort of assumed in all the practice problems we've looked at, we've assumed that the reactants are reacting in the compounds, the amounts that they need to react completely. But in reality, this doesn't happen very often. Right? In reality, one reactant is usually sort of the available in less quantity, and so it limits the amount of product that can form, and that's what we call the limiting reactant. And in a reaction, a limiting reactant is going to be completely used up. And there's going to be some of the other reactants that do not get used because the limiting reactant is gone and there's still some excess of them. Right. So I think that the book does a good job, and it shows this concept in terms of a sundae. And I think this is a good place to start to understand limiting reactants. Right? So if you define a sundae as 2 scoops of ice cream, 1 cherry, and 50 milliliters of chocolate syrup. Right? So say you're working at a restaurant and you have to make sundaes, and every sundae has 2 scoops of ice cream, 1 cherry, and 50 milliliters of syrup, and that equals 1 sundae. All right? So you can think of these ingredients as chemical compounds, as molecules in a chemical reaction.
right? You can think of them the same way. So you need 2 scoops of ice cream, that's the same as saying you need 2 molecules of something, right, to form one product molecule. Right? So what if you go into the restaurant and you had 8 scoops of ice cream available, 6 cherries, and 100 milliliters of syrup? How many sundaes could you make with that? Right? Well, you take, for one sundae, 2 of these, 1 cherry, 50 mils of syrup, that makes 1. 2 scoops of ice cream, another cherry, another 50 milliliters of syrup, that makes 2. Right? You could try to keep going. You have more ice cream, more cherries, but you just used up all your syrup. Right? So you can't technically make any more sundaes if they're defined by these 3 ingredients. Right? So in this example, the chocolate syrup is our limiting reagent. It's the compound that's there in the lowest quantity, and it gets used up first. The problems involving limiting reactant, there are 4 steps that you typically do to solve them. And I think some people teach what are called ICE tables. I'm not going to do that, but if you've been taught that, you can. They work. I like to think of them in terms of what we saw with the roadmap. So here are 4 steps you can use to solve some of these problems. Step 1, record what you have. You're going to be given enough information to know the number of moles you have of typically both or all your reactants. You're going to be given enough info to know that. The next step, you need to calculate what you need. Pick one reactant and calculate how much of the other you're going to need. Step 3, determine the limiting reactant and the excess reactant. So determine which is available in the smallest quantity. And then finally, step 4, you use the number of moles of the limiting reactant to determine the amount of product that can form. Right, so if we try a practice question with a limiting reactant problem, in a preparation of ClF3, we have 0.75 moles of Cl2 and 3 moles of F2. Which one of these is the limiting reactant? And write a reaction table. So your book likes to is giving us these reaction tables. Right, so balanced equation. Right, and so this is an animation. The balanced equation is Cl2 plus 3F2 goes to 2 ClF3. Okay, so that would be the first step. And that's really the first step of any chemical problem, is you have to make sure you have a balanced chemical equation. Right. The next step is you're going to determine how many moles can be formed of the product given the number of moles of each reactant. Right. So you're given 0.75 moles of Cl2. We use the molar ratio 2 to 1 in the chemical equation, and we determined that 1.5 moles of product can be formed. Now we look at F2, if we're given 3 moles of F2, right? And this is if we look at the molar ratio in the balanced chemical equation, now that would be 2 moles of ClF3 for every 3 moles of F2. So we multiply by that ratio, and we can have 2 moles of ClF3 formed for every 3 moles of F2. So which one of these is the limiting reagent? Well, you look at which one produces the lowest number of moles of product, and that would be Cl2. Okay. So you can also write these, what I think some people call these ICE tables. You have initial value, change value, and a final value, right? And so if we look at these, the initial for the limiting reactant and the change, right? So we had 0.75 moles Cl2. The change, all of that's going to be used because it's the limiting reactant, and the final value is going to be 0 moles. F2, we had 3 moles to start with, right? The change, it's going to occur, it's going to lose 2.25 moles. And again, you find that by multiplying this number by the ratio of the chemical equation, in the chemical equation, right? So when we subtract 2.25 from the initial value 3, what we get is 0.75. That's how many moles excess are going to be there of F2. And then the number of moles of ClF3 that are produced is 1.5. Right. So let's try another question like this. How many grams of CO2 gas form when 80 grams of I2O5 and 28 grams of CO are mixed? Right, so this, we're given the mass of both reactants. What we need to do is calculate the number of moles of both reactants. So to do that, we need the molecular weights. And those, again, important to know how to calculate them. I am just going to write them down. So molecular weight of I2O5 is 333.81 grams per mole, and CO is 28 grams per mole. Okay. And we're going to also need CO2, which is 44 grams per mole. Okay, so the first step is determine the number of moles you have. So we have 80 grams of I2O5, divide that by our molecular weight, and that's 0.024 moles of that compound. CO, we have 28 grams divided by 28 grams per mole. Yeah. And that equals 1 mole of CO2, CO. Right. So now we've converted from mass into moles. The next step is to determine which of these is limiting, right? And you can't simply look at, okay, I2O5 is a smaller number, so it's limiting, because we need to look at the ratios in the chemical equation. So the easiest way to do this is just to determine how many moles of CO2 can be produced from each of these numbers. So if we have 0.24 moles of I2O5, we multiply that by the ratio of 5 moles of CO2 divided by 1 mole of I2O5. And that gives us, let's do this quickly, 0.24 times 5, 1.2. 1.2 moles of CO2. If we look at 1 mole of carbon monoxide, multiply that by the ratio of 5 moles of CO2 divided by 5 moles of CO. So it's a 1-to-1 ratio. So that would produce 1 mole of CO2. Okay, so which one of these is limiting? Well, that would be the carbon monoxide, right? And if you just looked at the number of moles of each of them present, you wouldn't have chosen that one. You would have picked the I2O5. But it's important to take this all the way through, how much product can be produced by each of those numbers, right? So CO is limiting, so we're going to use this number in our calculating the rest of our calculation, right? So if we have 1 mole of CO2 and we multiply that by 44 grams per mole molecular weight, what we'll get is 44 grams of CO2 can be produced. Right. The last topic in chapter 3 is what's known as reaction yields. Right. So the theoretical yield is the amount of product that can be calculated using the molar ratio from the balanced chemical equation. Typically, actual yields in the real world are different, are less than the theoretical. And so the actual yield is just the amount of product that is actually obtained by a reaction. And you can calculate this, what's known as a reaction yield, a percentage yield, which you've probably may have done before if you've in high school chemistry, in high school chemistry lab. And that's where you take your actual yield of product, divide it by the theoretical yield, and multiply by 100, and you get your percentage yield. And so your theoretical yield, you find that very simply by the methods we've already been using in these practice problems. You use the number of moles that are present of a reactant and convert that into moles of your product, and that would be your theoretical yield. Right? And so why is the actual yield and theoretical yield different? Well, a lot of times you have a side product that takes away some of your reactants from making your main product. Okay, let's try last step. We're going to try a practice problem, right? Combustion of 10 grams of methane produces 19.8 grams of water. What is the percent yield of the reaction? Okay, so in this case, we're not given the amount of oxygen. You can assume oxygen is in excess, so that means methane is our limiting reagent. So let's look at methane. 10 grams of methane divided by molecular weight, 16 grams per mole. Oops. That equals 0.625 moles of methane. Okay, so how many moles of water can be produced by that number of moles of methane? Well, we use the ratio in the chemical equation. That's 2 moles of water produced for every 1 mole of methane. So we get, theoretically, we can produce 1.25 moles of H2O for 10 grams of methane. Okay. But we're given the amount of water produced as grams, so we need to convert this into grams. So 1.25 moles of water times the molecular weight, 18 grams per mole. That would give us 22.5 grams of water. That would be our theoretical yield. Now to calculate the percent yield, what we would do is take our actual yield, 19.8, divided by 22.5, our theoretical yield, and that would give us 0.88, so that'd be our fraction. Multiply that by 100, and that would be 88%. So our actual yield is 88% of our theoretical yield in this problem. Right. So that ends our chapter 3 material. Chapter 4 is sort of picking up with this chemical problem solving, but we're applying all these techniques that we learned in chapter 3 into aqueous chemistry. And you'll find that a lot of reactions that we're concerned with, especially biologically, occur in the aqueous phase, dissolved in water. All right.